Hello guys, this is tutorial 6, which is hydrology. So what we're going to be doing, we're going to be doing question 1 and question 2. Question 1, we're given that a 400 hectare catchment area situated near Newcastle in Natal, it's an inland region, has an average annual rainfall of 850 millimeters. The elevation of the point of at the head of the natural channel watercourse, which has a length of 2.8 kilometers, is a fairly uniform slope, and a fairly uniform slope is 1379 meters above sea level. The elevation of the discharge point is 1323 meters above sea level. We are told that the average slope of the hillsides in the catchment was calculated to be 11.8% over 65% of the catchment and 31% over the remainder. The soil permeability of the catchment area can be considered to be 25% semi-permeable, 35% permeable, and 40% very permeable. The catchment is covered by 30% dense timber plantations, 20% cultivated land, and 50% grassland. So we're told that we should use the rational method to calculate the peak discharge for 10-year, 20-year, and 50-year return period storms, and then we plot the graph at the end. So the first thing that we have to do, we have to calculate your runoff coefficient, which is C. We know that C for rural catchment, it's given by C, it's CS plus CP plus CV times FT. So first thing that we have to check the conditions that were given for surface slope. Surface slope will give us SC. So you have to check whatever you're given under surface slope. Unfortunately, you guys won't be able to see where I'm reading from. I'm using a different device. I didn't print out the papers. So we're told that the average slope of the hillsides in the catchment was calculated to be 11.8% over 65% of the catchment and 3.1% over the remainder. So we go down to our table. So we know that our mean annual rainfall is 850, so it has to fall between 600 on that table where 600 to 900, and then we know that it's hilly, and then it's 11 to 35%. So we're gonna get our first part, which is going to be 0.65% times 0.16, and then what else are we told? We are also told that and then we also add 35%, which is 0.35 multiplied by 0.03. 0.03 it's given there on your table. The table that's written rural in brackets is C1. It's next to, it's on that column of 600 to 900, and then you'll see the first one there on top. So you get your answer as 0.1145 as your CS, and then we go to CP, and then CP is permeability. We're told that, let's check what our statement is saying about our permeability. We are told that the soil permeability over the catchment area can be considered to be 25% semi-permeable. So 25% of that is going to be semi-permeable, and then 35% is going to be permeable, and then the 40% will be very permeable. So what you do, you go to your table, and then you check. They said the first 25% is semi-permeable, so we'll have 25% times the value that we get on the table for semi-permeable, which is 0.16 times 0.16, and then plus you're also told that the second 35% is permeable, so you're gonna have the 35% times the value that you get under permeable is 0.08, plus the other one is very permeable, which is 40% times 0.04, and then you get your CP as 0.084. And then now you go to your vegetation. What are you given for vegetation? Let me go read it for you guys again. We are told that the catchment is covered by 30% dense timber plantations, 20% cultivated land, and 50% of grassland. So you go to your table again. You say, okay, they say 30% is thick plantation. So we're gonna take thick bush and plantation on the table. We're gonna have 30% times 0.04 plus they said the second condition was 20% of light bush and farm lands. So we're gonna have 20% times 0.11, and then plus 50% of grasslands. So we're gonna have 50 into 0.21, and then you're gonna have your CV as 0.139. And then after this you get your big C. You know that C is given by this addition, so it's going to be 0.1145 plus 0.084 plus 0.139, so we'll have 0.3375. So now you have your C. After getting your C, now we have to determine the C for your return periods, like the adjustments. So you're gonna check. We're given that, I'm not sure if Sam made a mistake or what, but I'll just continue with whatever he gave me on the memo. Here we're told that it's a fairly the elevation of the point head, which it has a fairly uniform slope, and then he used the first table, which was adjustment factor FT for the steep and impermeable catchments. So he used that table where it says return period in years, and then you are given the adjustment factors, so you use the first row. So for return period of 10 years, you'll have this 0.3375 multiplied by the adjustment factor, which is 0.845, and then you'll have 0.287, and then for return period of 20 years, and then you'll have 0.3375 multiplied by 0.9, you'll have 0.304, and then return period of 50 years, you'll have 0.3375 multiplied by 0.95, and then you'll have 0.321. So after this, your next step is to calculate time of concentration, which is TC. Okay, first thing you have to calculate the slope of the water course. It's given by h, which is the difference in the elevation, divided by the length, multiplied by the 100. So your change in L, it's 1379 minus 1323, all divided by 2.8 times 1000, so that you work with both meters. You can choose to change this one to kilometers or choose to change kilometers to meters. So what you will have now, you'll have a slope of 2%. And then now what you do, you have to calculate concentration time. We know that TC is given by 0.87 times L squared divided by 1000 times S, all to the power 0.385. So you have 0.87 times your L. Your L now you take it as kilometers squared, and then you divide by 1000, then you change your slope to decimals in 0.02, and then all to the power 385, and then your time of concentration is 0.66 hour. And then from there you go to the next step. The next step is the graph part. I'll show you guys from my laptop how they did this. So what they did here, I'm not sure if you guys can see it proper. I have a flash on. So what they did, they took the concentration time, which was 0.66. You come here, this is 0.1. So if this number here, it's 1, you can count how many lines you have here. You have 1, 2, 3, 4, 5, and then 6, 7, 8, 9. So which means this is 0.2, 0.3, 0.4, 0.5, 0.6. So that's how they count them. When you come here, you do the same thing. This is 10. You check how many lines you have here. So this, I think it's gonna be like 1, 2, 3, 4, 5, 6, 7, 8, 9. I think this is gonna be 2, 3, 4, 5, 6. Sorry about that. I was showing you how to know exactly where to put this. I was saying this is 0.1, this is 1. So how many lines do you have here on this log scale? This is 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is gonna be like 2, 3, 4, 5, 6, and then 7, 8, 9, and then 10. So 0.2, 0.3, 0.4, 0.5, 0.6. That's where they had 0.66 between these two lines. And then you draw, you are told that it's an inland region. Where this line touches your inland region, you draw a horizontal line to your left, and then you're given the return periods. So after getting that return period, so what you do, you draw where it touches 10 year, you draw a line going down to your next graph. And then now you come here to your graph. I don't know if you guys can see. I'll just, you are given the annual like rainfall. So we have 850, we have 800 here, we have 700 there, and then I think it's between here, I can't see properly. I think that's 800 and 900 here. You draw a line between those lines, parallel to those lines. You see the blue line there, and then there you go to your 10 year, you draw a line going down where it touches that blue line. You draw to your right, and then you read the millimeters on your right. You do the same thing. You come to 20 years there, you go to 20 years, you draw a line up until it touches your blue line. You read your value on your right. You do the same thing for the 50 year. So that's how they read those values. And then now this is the values that they got. Your value can be off, it's still fine, you can still have those ones. And then after, you have to calculate the intensity of each return period. So I for 10 year is given by D for 10 year, and then divided by the time of concentration. So we got 51 divided by 0.66, and then you have 77.3 millimeter per hour. And then I20, intensity for 20 year return period, is D20 divided by TC, then will be 60 divided by 0.66. We have 90.9 millimeter per hour. and then I50, it's D50 divided by TC. It's going to be 0.8. It's going to be 84 divided by 0.66, and then you'll have 127.3 millimeter per hour. So now after getting this, you have to get your peak discharge for each return period. So we have Q10. We know that Q is given by CIA divided by 3.6. So what you do now, you go to, so now for Q10, you're going to use the C that you got for your 10-year return period. I'm talking about this C. This is the C that I'm talking about. For each and every return period, it has its own C. So we'll have 0.287 times 70 times 77.3 times 4. That was the area, and then you divide by 3.6, and then you get your discharge for 10-year return period to be 24.6 meter cube per second. And then you go to Q20, you do the same thing. It's going to be 0.304 times 90.9 times 4, which is the area, divided by 3.6. You'll have 30.7 meter cube per second. You go to Q50, you have 0.321 times 127.3 times 4 divided by 3.6. You'll have 45.3 meter cube per second. After this, what you're just left to do is to produce a graph. This is how the graph looks like. So what they did, they drew peak discharge versus return time. So what they have there, they have the 10-year period of 10. They correct the Q was 24.6. They draw it there, and then 20. They have 30.7. They draw it there, and then 50. They draw it there. So this graph, I'll even share the memo with you guys. So the next thing that we have to do, we have to go to question 2. I think I'll upload a video on question 2 so that this one doesn't take too much time to upload.